All right, so we're going to talk about ellipses today. And we're going to do with ellipses exactly what we did with circles and with parabolas. We'll talk about them as conic sections. So let me grab a picture. So an ellipse you get when you cut your cone at an angle to the base. So this curve here would be an ellipse. If you cut the cone parallel to the base of the cone, you get a circle. So ellipses and circles are very closely related. And we'll see that in their equations also. So this is why we call an ellipse a conic section. So we're going to talk about the locus definition, and then we will talk about our equations that the locus definition gives us. So an ellipse is the locus of points. And just a reminder, a locus is a set of points. So I'm being kind of repetitive here when I say locus of points. I just want to re-emphasize we're talking about points. Locus of points in the plane. So that the sum of the distances there's that distance that's a big thing with conic sections. Sum of the distances from two fixed points, and the fixed points are the foci, is constant. So the sum of the distances is constant. So let's draw a picture here, what this is telling us. So an ellipse looks kind of like an oval. My ellipses never turn out beautiful and perfect, but we'll get the idea. There's an ellipse-ish. And the ellipses have two foci. Foci is plural of focus. So this is a focus, and this is a focus. And what this definition is telling us is if I go to any point on the ellipse, and I'm going to name each one of these distances. So we go to a point on the ellipse. I'll call this D1. And that D2. What this definition is telling us is that D1 plus D2 is a constant. So just to contrast this with the parabola, for the parabola we said the distance from the point to the directrix and the point to the focus, those two distances were the same. Here we're saying we add these two distances together, and that's always a constant. So what we do to come up with our equation is we write the distance formula between the focus and that point, between this focus and that point, rearrange it a little bit, and we get our equation for our ellipse. All right, questions so far? All right, the next, yes?
So the constant, like, what does that exactly mean? So is it just a number? Are they all like equal? Or, I don't know.
For a particular ellipse, that there's a number that if you add those two distances together, you'll always get that number.
Oh, no matter where on the...
No matter where on the ellipse.
Thank you.
Okay. All right, so I want to talk about the parts of an ellipse, and then we'll talk about our equations. All right, so there is a generic ellipse. This point is a focus. This point is a focus. This point is the center. And we have a vertex at each end. So this is a vertex. And then we have co-vertices, or minor vertices. So our major axis is the long axis. The minor axis is the short axis. The distance from the center to a co-vertex we call B. The distance from the center to a vertex we call A. And the distance from the center to a focus we call C. And I'm going to draw in one extra piece here from the co-vertex to the focus. So I have this nice right triangle here that I'm going to highlight in blue. This hypotenuse of the right triangle is also A. So if we took this piece here and slid it up there, it would fit perfectly there. For an ellipse, A is always greater than B. The major axis is always longer than the minor axis. And from this nice little right triangle here, A squared equals B squared plus C squared. This side is B, this side is C, the hypotenuse is A. So if you can visualize that little triangle, you'll remember this relationship. And that's an important one for an ellipse. A is always bigger than B, the major axis is always the longer axis, and A squared equals B squared plus C squared. So those are our parts. And what we're going to do, just like we did for our parabola, we're going to write our equations for a vertical and a horizontal major axis. And these A's, B's, and C's tell us the distance that we move from the center to these various pieces. And the kinds of problems that we end up doing with ellipses are exactly the kinds of problems we did with parabolas. There's a lot of repetition in Chapter 9. We end up doing the same kinds of problems. All right. Are we good so far? Okay. So we're going to talk about our standard equation for an ellipse. And we'll start with a horizontal major axis. So let me grab a picture again. So we're talking about this ellipse. Our equation is x minus h squared. So it starts off looking like a circle over a squared plus y minus k squared over b squared equals 1. So it's a lot like the equation of a circle. The way that we can tell that our major axis is horizontal, A is bigger than B. The bigger number is under the x part. A is the bigger number. A squared is going to be bigger. It's under the x part. That tells us that we have a horizontal axis. Our center is at the point HK, just like a circle, and is very similar to how we describe the vertex of a parabola. Our major axis Well, this piece is A. This piece is A. So the length of the major axis is 2A. The minor axis. This piece is B. This piece is B. So the minor axis is 2B units long. The foci. To get to the foci from the center, we have to move left and right. And the distance that we move left or right is C. So our foci are going to be H plus or minus C, K. So we're going left and right C units from the center to get to the foci. So C units here, C units there. The vertices. A tells us how far from the center to go to get to the vertex. And we have to go right and left. So we get H plus or minus A. Okay. The co-vertices. B tells us how far from the center to go up and down, in this case, to get to the co-vertices. So those coordinates are going to be H, K plus or minus B. We go up and down to get to the co-vertices. And I'm going to draw this nice little triangle here. That hypotenuse on your little right triangle is A. And for an ellipse, A squared equals B squared plus C squared. So that's the relationship between those distances that we're talking about here. All right, questions so far? So for the vertical major axis, really all we're doing is turning the ellipse the other way, and instead of going left or right, we go up and down. So we just switch those. Everything else stays more or less the same. All right, so let's talk about a vertical major axis. So for this one, I'll get a different picture. Everything is the same, all the distances. We're just turning our ellipse. Our equation, y minus k squared over a squared plus x minus h squared over b squared equals 1. And we still have a greater than b. So the way that we tell that our major axis is vertical is the bigger number is under the y. A is bigger, it's under the y part. Our center is still at HK. Our major axis is still 2a units long. From here to here is 2a units. Our minor axis from here to here is still 2b units long. Our foci. Well, this time, to get to the foci from the center, I have to go up and down. And C tells us how far to move up or down. So I'm going to go h k plus or minus c. My vertices. A tells us how far to go from the center to get to the vertices. I'm going up and down to get to the vertices from the center. H, k plus or minus a. The co-vertices, or the minor vertices, now we have to move left and right to get to the minor vertices, and we go b units. So that's going to be h plus or minus b, comma, k. And I can draw in my nice little hypotenuse here. That length is still a. So we get a squared equals b squared plus c squared. Always for an ellipse. So the kinds of problems that you end up solving with ellipses are very similar to kinds of problems you solved with circles, very similar to kinds of problems you solve with parabolas. You'll be given some subset of these pieces of information, and you use that to figure out the other pieces of information. So the kinds of problems you end up doing are really the same kinds of problems over and over, just for different shapes. You're just given different combinations of pieces of information, and you have to use these relationships to figure out the other piece of information. Questions? Okay, let's look at a couple of examples of the kinds of questions that you're going to be looking at with ellipses. Let's find the center, the vertices, and the foci. Of the ellipse 9x squared plus 4y squared equals 36. Now the key here, just like with parabolas, is the first thing we want to do is write it in standard form. So what do we need to do to get this thing in standard form? We need a 1 over here, so we're going to divide everything by 36. I'm going to write this out explicitly. So we get 9x squared over 36 plus 4y squared over 36 equals 36 over 36. Dividing everything by 36. Well, I get x squared over 4 plus y squared over 9 equals 1. Well, now we have everything. Where is our center? Center is at 0, 0. This is x minus 0 squared, y minus 0 squared. Is this vertical or horizontal? Vertical. This tells us, since the bigger number is under the y, this tells us it's vertical. And a equals, this is a squared, 3. B equals 2. And we know that a squared equals b squared plus c squared. So c squared is 9 minus 4. So c squared is 5. And c is the square root of 5. Well, now we can find, so there's our center, our vertices. We're going to go up and down from the center to get to the vertices. So we're going to be at 0 plus or minus 3. Our co-vertices, we're going to go left and right from the center to get to the co-vertices. So plus or minus 2, 0. And our foci, we need to go up and down from the center to get to the foci. So we're going to get 0 plus or minus square root of 5. And if we drew a little sketch of this, our ellipse, there would be my center. There would be a point at 0, 3. There would be a point at 0, negative 3. There would be a point at 0, 2. And there would be a point at 0. Sorry, did that backwards, didn't I? Negative 2, 0. This should be 2, 0. And I could sketch a little sketch of my there's a rough sketch of that ellipse. And if you did a sketch something like that on a quiz or a test, that would be fine. And all of our questions are some combination of this information to find out other pieces of that information. All right, questions? All right, let's look at another one. We want the equation. This is going to be a standard form. We have an ellipse with major axis 10, foci at plus or minus 3, 0. What I suggest for a problem like this is draw a little picture, just like we did for our parabolas. Well, the foci are at plus or minus 3, 0. So there's a foci at 3, 0, and there's a focus, sorry, minus 3, 0. Is this going to be vertical or horizontal? Horizontal. The foci are on the major axis. So we know already it's a horizontal. Where is the center? In the middle. What's halfway between negative 3, 0 and 3, 0? The center is at 0, 0, halfway between the two foci. What does this tell us? If the major axis is 10 units long, A has to equal 5. What does this tell us? If the center is at 0, 0, C equals 3. And we know that A squared equals B squared plus C squared. So B squared, which is what we need for our equation, is 25 minus 3, or minus 9. A squared minus C squared. So B squared is 16. So our equation, x squared over, it's horizontal, so the bigger number has to go under the x part. 25 plus y squared over 16 equals 1. So this is kind of like what you're going to do for your conics project to come up with your equations. You'll know where your center is for your ellipse. You know where the vertices are, and use that information to come up with your equation. All right, questions there? All right, this next one I think you'll enjoy quite a bit. We want to sketch a graph of the ellipse (25x squared plus 9y squared minus 200x plus 36y plus 211 equals 0. So for now, you'll have to take my word for it that this is an ellipse. Tomorrow we'll talk about how we figure out, looking at an equation like that, that it's an ellipse. But what do we need to do here? Yeah, that's a minus sign. We need to get it in standard form. So I'll collect the x parts. And I'm going to put the negative 211 on the other side. Now what do? Complete the square twice. So I'm going to complete the square on the x part and on the y part. Yeah, thank you. Exclamation point there. So I'm going to write this as 25. I'm going to factor out that 25. X squared minus 8x. We'll complete the square there, plus 9 y squared plus 4y equals minus 211. I should have left a little more room here to put all my numbers here. And I'm going to complete the square here. Divide 8 by 2, I get 4. And I'm going to add a 16. And I remember that the 25 is being distributed to the 16. So I need to add, what I'm adding here is 25 times 16, which is 400. And then I complete the square here, divide this by 2, so I get 2, add 4. And I remember that the 9 is multiplying the 4. So what I'm adding here is 36. So, yes. No, I'm adding the same thing to both sides. I'm adding 400 to the left, so I need to add 400 to the right. Before, when we were completing the square, we had everything on the same side of the equation, so I added and subtracted on the same side. All right, so we get 25. This is a nice perfect square. X minus 4 squared plus 9, y plus 2 squared equals, and when I do this arithmetic, I end up with 225. Still not quite in standard form. What do we do to get it in standard form? We want a 1 here, so we're going to divide everything by 225. When I do that, I get x minus 4 squared over 9 plus y plus 2 squared over 25 equals 1. And now I have everything I need. My center is at -2. -2. Thank you. Is this vertical or horizontal? Vertical. This tells me it's vertical. The bigger number's under the y part, so it's vertical. A equals 5. B equals 3. So I can make a little sketch here. It's going to be a rough sketch. So here's my center at 4, -2. I'm going to go up and down 5 units from the center to get to my vertices. So I go up 5, I get 4, 3. And I go down 5 from here, I get 4, -7. And I go left and right to get to my co-vertices by 3 units. So this is going to put me at 7, -2 when I go right. And I'll be at 1, -2 there. And then my ellipse is going to look roughly like that. There's a rough sketch of that ellipse. That would be fine for a sketch of that ellipse. You know where the axes, where all the vertices are. You know where the center is. You know it's vertical. So it's a lovely ellipse. Well, it didn't. All it just asked us to do is sketch a graph. So if we sketch in a graph, we don't have to put the cosine. Yeah.
So if it's like an ellipse and we divide and complete the square twice and everything, will it come out to one exactly every time?
Yeah. So for our standard equation, we want to get a 1 here. Right. So you divide by whatever's going to give you a 1 on that side.
Okay.
So since I wanted a 1 here, I divided everything by 225.
Oh, I see.
So I divided both sides by 225. That gave me a 1 there. 25 divided by 225 is 1/9, and 9 divided by 225 is 1/25.
Okay, thank you.
All right, the last thing that we need to talk about for today is there's a way to tell how stretched or how close to a circle an ellipse is, and that's called the eccentricity. And we'll talk about eccentricity of other kinds of conic sections as well eventually. Eccentricity is C over A. So it's a ratio. It talks about how close the foci and the vertices are to the center. For an ellipse, the eccentricity is going to be between 0 and 1. If it's close to 0, that means that the foci are very close to the center. This C number is very small. It's almost circular. So my ellipse is going to look like that. And my two foci are going to be close to the center. If it's close to 1, my ellipse is flat. So my ellipse is going to look like this. And that means the foci are close to the vertices. C and A are close to being the same number. And it turns out that ellipses are very important because the orbits of planets are not circular, they're elliptical. And the sun is at one focus of the elliptical orbit.
What's out the other?
Not a physical object. So something like a comet is going to have an orbit like this. It's going to be away from the sun for a long time, whereas a planet is going to be closer to a circular orbit. All right, questions there. Really quickly, the reflective properties, or property. The way that the reflective property of an ellipse works is if you have a room, a building, and these are our foci. If you have a light source, a sound source, a radio source, something at one focus, it's going to reflect to the other focus. So they make what are called whispering chambers. I think there's one there's somewhere in the Capitol in Washington, D.C., where if one person stands at one focus of the ellipse and another person stands at the other focus, and the one person talks, you can hear the other person. It's like they're standing there whispering in your ear.
What? But they're in the same room though.
This could be separated by a bunch of bookshelves or something. As long as one person's at one focus and one person's at the other focus, you can hear them talking.
What's the monument?
I can't remember what the building is. I was on the campus of University of Nebraska. I was at a conference. They have a sculpture. So the sculpture is on either side of a sidewalk. And the sculpture, if you look at it from the side, were these two big pieces of metal. And the sidewalk kind of went through the middle here. And the big pieces of metal were elliptical shaped. And if you stood at one focus, so as you went through here, if you stood at one focus and another person stood at the other focus on the sidewalk as you walked through there. So this is the sidewalk. One focus is here, one focus is there. You could stand here and talk facing this direction, and this person could hear you. It was like they were standing there whispering in your ear.
So it's like echoes?
Sort of.
So it's like small echoes.
It is an echo, it's a reflection. But yeah, it's really cool. So.
Do they have the foci marked out?
No. But we could, when we were all math people, so when we walked through, we're like, this is an ellipse, let's find the foci.
Oh my goodness.
All right. Yes. They reflect from multiple points, but it always reflects back to the focus, and because the sum of those distances is always the same, it comes in as one sound, not a bunch of different sounds, because the sound's traveling the same distance, no matter what. All right, homework. You had to be at the focus.
Oh. What if the focus was small enough so you could touch your face and your mouth?
All right, what time do we get out of here? All right, once everybody has this written down, I'll show how to construct an ellipse with a string.